When we talk about acids and bases, there are some distinguishing characteristics we can look at to figure out which type of chemical substance we have. So whenever we're talking about acids, they're going to have a sour taste. All of our citrus fruits like oranges, grapefruits, lemons, limes, things like that are going to be very acidic. They definitely have a sour taste to them. Acids react with metals to produce hydrogen gas, H2. So for example, if you take zinc metal and you react it with an acid like HCl, okay, the hydrogen here is going to be released as hydrogen gas, and then what you're left with will be the zinc and the chlorine, and to make the charges balance out, zinc has a positive 2 charge, chlorine with a negative 1 charge, you'd have to have 2 of them pair up there. So if we wanted to balance our equation, we'd just throw a 2 as a coefficient in front of that HCl. So that's an example of how it can give off hydrogen gas whenever it reacts with metals. Acids will react with carbonates, things that end with CO3, in order to produce carbon dioxide. So if you had like calcium carbonate, chalk, or limestone, then whenever you add an acid to that, like vinegar, then it's going to bubble and fizz and give off carbon dioxide gas. Whenever you use an indicator, indicators are different things or a substance which will change color in different types of solutions. If you have litmus paper, okay, litmus paper will turn red. If it's red, it'll stay red. If it's blue litmus paper, it'll turn red. And I tend to think of acids as things that can burn you. Bases can also burn you just as badly, but we tend to think about acids as burning your skin. And the color I associate with burning is red. So if it's turning it red, it's an acid. And if we use the indicator phenolphthalein, the solution will remain clear and colorless. Acids are going to have a pH value less than 7, so between 0 up to 7 or 1 to 7, depending on which pH scale you look at, but it will be less than 7. Can cause severe burns. We know it can damage our skin if it's a strong enough acid because it's very corrosive. That's the word you use to describe things that can eat away at something else. And whenever they react to produce hydrogen ions because all of our acids in general begin with H, hydrogen. So you can pull off that hydrogen and that hydrogen ion is then released. So you have some examples here. We've got HCl, H2SO4, HNO3. They're all different examples of acids. There is one acid which does not begin with an H, and that's going to be CH3, COOH. Okay, in this case, the hydrogen is tacked on there at the end, and that's going to be acetic acid, which is the main acid that's in vinegar. Okay. When we talk about bases, instead of being sour, they're going to have a bitter taste. They're typically used to help for cleaning, so different cleaning supplies are usually pretty basic. And if you've ever gotten soap or shampoo in your mouth accidentally, you know it has a bitter taste to it. And the bases will also feel slippery. They're going to turn litmus paper blue. If it's red, it'll turn to blue. If it's blue, it stays blue. And that's easy to remember because base, blue, they both start with a B. They're both 4 letters. Base blue. And when we use phenolphthalein indicator, it's going to turn a magenta or a hot pink color. So it stayed clear and colorless when we put it with an acid, but it turns a very bright pink whenever you add it to a base. pH value will be greater than 7, so now it's above 7. They can cause severe burns just as much as acids can. They will react to produce hydroxide ions because in general our formulas end with OH. We've got NaOH, BaOH2, etc. There's only going to be one base that we're going to talk about that does not end with OH, and that's going to be NH3 or ammonia. Now, a salt, we tend to, whenever we say salt, we tend to be talking about table salt, the stuff we put on our food, which is going to be NaCl specifically. But in chemistry, when you talk about a salt could be any ionic compound, okay? Which means that it's either going to be a metal or ammonium, NH4+, combined with nonmetals. So NaCl is an example of that because Na is a metal, Cl is a nonmetal, but it doesn't have to be those. We could have K, potassium, paired with bromine, KBr. You could have calcium paired up with a polyatomic ion made of nonmetals, okay? You just have to have metal and nonmetal paired up in order to have that salt or ionic compound formed. So those are the distinguishing characteristics between acids and bases. The next part we're going to look at is how you name these. That's what nomenclature means. That nomen part there at the beginning means name. So when we name bases, we name them just like any other ionic compound we've dealt with this year. So we look at the first element, the metal, and we write the name for it. So Na is sodium. And the metal will need a Roman numeral after it indicating its charge. If when we look up at the table, it's one of those question mark charges, one of the ones that can take on multiple charges. But we look up sodium, it's in group 1. They always ionize to have a +1 charge, so we don't have to write that. Anyone with a periodic table could know that. So we're not going to include it. OH is a polyatomic ion called hydroxide. So our base name is sodium hydroxide. For the next one, we start with our metal, barium. It's in group 2. It always has a +2 charge because of that, so we don't have to use a Roman numeral. And then we've got OH. It does not matter that there's 2 of them. We still just write hydroxide. The next one, we have Fe, which is iron. And when we look up iron, it's a transition metal. It's there in the middle where we know it has a positive charge, but the actual number can change. It's plus question mark. So the way we're going to figure out what the charge is we're going to look and see how many hydroxides we have. Because hydroxide has a charge of -1. So if we have 3 of those, then this whole half has a charge of -3, which means that this half has to be a +3. So once you kind of see what's going on there, then ultimately you can just look and see what the subscript is on the hydroxide, and that will tell you what charge you're going to put in Roman numerals for the metal. And it still is just hydroxide. Now this last one does not end with OH, so we can't name it this way. It is our exception, and its name is ammonia. All the other bases, though, will follow the pattern of the first 3 that we saw. The rest of this is about naming acids. There are a lot more rules. It depends on what kind of elements you have, how many different elements are being paired up. Whenever we have a binary acid, bi means 2. So that means it's going to be hydrogen and something else right after it. So we're going to use this general template to write our names. We're going to start with the prefix hydro. So for this first one, HF, we're going to start with hydro. And then we're going to put the root for the element. And the root is sometimes just the shortened part, the very beginning of the element name. Sometimes it's the whole element name. And you kind of learn them as you come across them. So for fluorine, our root is just going to be fluor. We leave the INE off. And all of our halogens follow that same, the same thing. Chlorine will be chlor. Bromine will be brome. Iodine would be iode. We just leave the INE off the end. So we have hydro and then fluor. And then we have IC as our suffix. So we'll put ic at the end, and then we have the word acid. So HF is hydrofluoric acid. So we'll do the same thing with this one. We start with hydro as our prefix, and then we need the root for chlorine, so that's just going to be chlor. And then we put our suffix ic, and then the word acid. It doesn't matter that we start with 2 hydrogens, it still starts with hydro. And then we need the root for sulfur, which is actually just sulfur. Sulfur is the whole name, carbon is the whole thing. The root for carbon is carbon. If it's phosphorus, it's just phosphor. You leave the us off the end there. But that only gets us part way done. We got through the root. Now we need to end it with our suffix ic and the word acid. So that's hydrosulfuric acid. That's whenever you have two elements, hydrogen and one other. If you have an oxy acid, that's your clue that you're going to have oxygen with it. These are tertiary acids because there's going to be three parts to it. We're going to start with hydrogen, we're going to have something else, and then we're going to have some number of oxygens there at the end. And I put that X to represent a number and made it look like I was putting OX for oxygen, but that just represents the fact that there's going to be some number that we'll have there if it's more than one. Okay? So if you have halogens, carbon, nitrogen, anything like that combined with your hydrogen and oxygen, then this will be the process that we follow. And we'll see this most often. If you have only one oxygen, this prefix hypo means low. So the lowest number of oxygens will be hypo, like hypoglycemia is low blood sugar, hypothermia is low body temperature, hypo, low oxygen. Then we'll put our root, and then our suffix will be OUS. So for this first example, there's only one oxygen here at the end. So we start with our prefix hypo for low. Then we need our root. It's fluorine, so it's going to be fluor. And then we put our suffix OUS, and then the word acid. So it's hypofluorous acid. If we have two oxygens, the only difference is that we lose this prefix. There's nothing here at the beginning. We just start with the root and the suffix OUS. So the last one here is going to have, actually no, we don't have an example with only two. Let's make one up. Let's say that we have HClO2. Okay. So we're not going to have a prefix at the beginning. We're going to go ahead and have our root. So for chlorine, it's just chlor. And then we have OUS at the end. OUS. And the word acid. So it's chlorous acid. If we have three oxygens, we still don't have a prefix. We still start with the root. And this is where our suffix at the end changes to IC. So we have a couple of examples here that have three oxygens at the end. So no prefix. We're just going to start with the root for nitrogen, which is NITR. We leave off the ogen. Our suffix is IC, IC, and then the word acid. So HNO3 is nitric acid. We'll do the same thing here, even though it's H2 at the beginning. It doesn't matter. We're still going to start with the root. The root for carbon is carbon. We have our suffix ic, and then the word acid. So that is carbonic acid is how you say that. Okay, for the last one here, if you have four oxygens, we're going to start with this prefix per. Per goes with 4. Then we have our root. Bromine is going to be brome. And then the ending IC, acid. When you take your test, I will give you this chart. So you just have to be able to use that to come up with these names. There are a few exceptions to these rules, and they have to do with sulfur and phosphorus. And I will give you these as well. Anytime you have sulfur or phosphorus as that middle element, you pretty much are using the rule for the number of oxygens that come before it. So for example, if it ends with 3 oxygens, it shouldn't have a prefix and it should end with IC. But we see that it's ending with OUS like if it only had 2 oxygens. For sulfuric acid, it has 4, so we would think it would be per sulfuric, but it doesn't have that prefix there at the beginning. There's nothing there. It's just sulfuric, which would be the name if we followed the rules if there were only 3. So it gets off just a little bit for those two, and because of that, I'll give you those exceptions. But you do need to know on your own this last one. Acetic acid is the one that doesn't follow the rule of starting with hydrogen. The hydrogen is going to be here at the end instead. CH3COOH. So if you have a whole bunch of stuff mixed together, first you have to be able to distinguish, is it an acid or a base? And a quick way of knowing if it's an acid is if it says acid. So all of these here are going to be acids. So that means that the others, if it ends with hydroxide, means it's going to be a base. And those are the easiest ones to name, so let's go ahead and name those first. If I have aluminum, I have my symbol for aluminum, Al, and then I have hydroxide, which is OH. But when you're writing the formulas for these, you have to think about what the charge on this metal is, because the charge on the metal will help you figure out how many of these OHs will be tacked onto the end. So we look up Al on our periodic table, and it's going to be in the +3 column. So if we have 3 for our charge there, hydroxide only has a charge of -1. So that means that we have to take this charge, and that's going to become the subscript on our hydroxide. We have to have 3 -1 hydroxides to balance out the +3 on the aluminum. And you can't just write AlOH3 like this, because in that case, the 3 is only on the hydrogen. We want to have 3 of that whole thing, of the OH group. So for this last one, copper is Cu. It tells us right here its charge is a +2. So that tells us that we're going to have 2 hydroxides here at the end. So we put OH in parentheses, and we have 2 of them. If it's something with just a +1 charge, like sodium hydroxide, sodium's charge is +1. So you would just have NaOH. You don't put the hydroxide in parentheses unless you have more than one of them. Okay. So all the rest of these that we have left, we know are acids. And the first thing I look for is that prefix hydro. Because remember up here, hydro was when it was just hydrogen and one other element, and that was it. So we look for hydro, and we've got it right here. So that means it's going to start with H, and we have one other element, and it says bromic. So think about what element brome goes with, and that's going to be bromine. And that's it. All of our acids we know, except for acetic acid, our exception here, are all going to start with hydrogen. So we can go ahead and fill those in. We know that all of them will have another element based off of this root. So chlor is chlorine, fluor is fluorine, phosphor is P, phosphorus, brome is bromine, iode is iodine. Okay. Then, if it does not start with hydro, because that was only 2 elements, if it has any other naming, then we know it's going to have some oxygens at the end. And the number of oxygens we can figure out from looking at the prefixes and suffixes. So let's go ahead and throw some oxygen on each one of these. And then we'll use our rules right up here in this box to figure out how many oxygens are there. So our second one here, perchloric acid, whenever it starts with a per, if we look at our rules up here, when it starts with per, that tells us it has 4 oxygens. So that's going to be HClO4. The next one doesn't have a prefix, but it ends in IC. So when we look at our rules, when there's not a prefix and it ends with IC, it means we're going to have 3 oxygens. This next one, we could go and look at our rules, but we should notice that it's got phosphorus, and we've got an exception here with phosphorus. So if we just go and look and see what phosphoric acid is, we'll see it's H3PO4. So we'll put those subscripts in just from looking at our exceptions there. Okay. Hypo Bromus, we've got that prefix hypo, remember that, which means low, and that means that we have only 1 oxygen. So we don't write a 1. Okay, remember we're not going to have 1s written as subscripts, it's just implied. Just HBRO. And then finally we have iodous acid. It doesn't have a prefix, but it does end with OUS. So we go and see which one matches that. There's no prefix. Ends with OUS. So that's 2 oxygens. So we'll put a 2 right there after it. I'll do a couple on your assignment to get you started here. The exceptions are going to be number 2, number 8, number 9, and number 12. These are the ones that are not going to follow the rules that you'll need to look at your exception list for. Okay, and number 7. Sorry. Okay. On the bottom part, we're going to do what we were just doing, coming up with the formula from the name. And the exceptions that we're going to have down here are going to be number 5, number 4, and it looks like it's it. So, first thing I would do is go through and label them as either an acid or a base. And we know it's going to be an acid whenever it starts with a hydrogen. So we've got acid, 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 base. Base is going to end with OH. Acid again because it starts with H, and base. The ones that are bases, we name them just as is. On number 4, K is potassium. And OH is hydroxide. I don't need a Roman numeral after potassium because I know potassium's charge when I look it up on my table. It's +1 on my periodic table. Okay. For the acids, you're going to look and see, do I have oxygens at the end? If you don't have any oxygens, like on number 1, remember that's going to be when you start with the prefix hydro. And then we need our root. The root for sulfur is sulfur. And then we have our ending IC. And then the word acid. If it does have oxygen at the end, remember we have that box of rules. So on number 3, when you have only 1 oxygen, that's the lowest amount. So we start with the prefix hypo for low. Then we have our root for iodine, iode. And then it ends with OUS for the suffix. And then the word acid. In the second part here where we're writing the formulas, you don't really have to go through and label these as acids or bases because if it says acid, it's an acid. If it doesn't, it's a base. So iodic acid, we know acids start with hydrogen. We know we're going to use that root to figure out what the second element is. And then if it does not start with hydro, then we also know we have some oxygens. So we look and see if it's IC, how many oxygens are going to be attached there, and that means we're going to have 3 of them. Okay. On number 2, we've got calcium hydroxide. We put the symbol for the metal. Hydroxide's OH. You just have to check and see what the charge on that first element is, though. Since this is a +2, that means we're going to have 2 hydroxides paired up with it.